So for this lecture, we'll be discussing section 2.5, roots and radicals. Okay, so let us start with this definition. The principal nth root of a real number a, where a is greater than or equal to 2, is an integer, symbolized by this symbol. You look at this. So we have this symbol, and then there's an n here, and then there's an a inside this guy. Okay, so this is read as nth root of a. So this is read as nth root of a, or the principal nth root of a, and this is defined as follows. Okay, nth root of a equals b. Okay, nth root of a equals b means a is equal to b to the n. Okay, so nth root of a equals b means a equals b to the n, where a and b are both greater than or equal to 0 if the value of n here is even. Okay, so a and b are both equal to 0 if the value of n here is even, and a and b are any real numbers if n is odd. Okay, so again, we have nth root of a equals b, means that a is equal to b to the n. Okay, where a and b are greater than or equal to 0 if n is even, and a and b are any real numbers if n is odd. Okay, in other words, when this guy here is defined, okay, when this guy here is defined, then the value of this nth root of a is the number that, when raised to the power n, gives a. Okay, so the value of nth root of a, which is b, so this is the number when it is raised to the power n, it gives us the value a. Okay, so nth root of a equals b means that a equals b to the n. Okay, so to understand this better, let us consider the following remarks. First, if a is negative and n is even, then nth root of a is not defined. Okay, if a is negative and n is even, then the nth root of a is not defined. Now, when it is defined, the principal nth root of a number is unique. Meaning, if this guy here exists, okay, so whatever n is, n even or n odd, and whatever a is, so that value must be unique. Okay, so meaning, if we go back to this definition, if we have this equality, so nth root of a, this b is unique. There is only one possible value for b. For, look at this, principal nth root of a number. Okay, principal nth root. And we will always talk about principal nth root. So a lot of times we'll just drop the word principal. We'll just say nth root of a real number. Okay? Now, the symbol, this guy here, for the nth root of a, we call this radical. We call this radical. Okay? And then the integer n, the n that we see here, is called the index of the radical. So index. And then in here, a is called the radicand, the one that is inside the symbol. Okay? So this symbol, we call it radical. The n that we see here is called the index. And the number a there, the one that is inside the symbol, we call it the radical. If the index of the radical is 2, meaning if n is equal to 2, we simply write that symbol as this guy. So we can remove the value 2 there. Okay, so when n equals 2, we can just remove that 2 and simply write it this way. And we call this square root of a. Okay, not, well, you can also say second root of a, but for this case, we'll just say square root of a. Okay, and then when n equals 3, when the index is 3, okay, we call this symbol the cube root of a. Okay, cube root of a. Others may call it third root of a, coming from this notation, third root of a, but normally we call it the cube root of a. Okay? Now, let us consider these examples. So first, we have here fourth root of 16. Okay? So fourth root of 16, the complete solution is already here, but let us work one by one or step by step. So according to the definition, the fourth root of 16, this is some number b. Okay? And this means, so let me use this symbol and I'll write for the meantime what this symbol means. So it means. Okay? This means that 16 must be equal to b to the 4. Okay? 16 must be equal to b to the 4. So what is the value of b here? So that b to the 4 equals 16. Now, this is what we know. This is what we know. 16 can be written as 4 times 4. Okay? And this can also be written as 2 times 2, 2 times 2 times 2 times 2. Okay? And therefore, this is equal to 2 to the 4. Okay? And that's what we see in here. Okay? So 16, it's equal to 2 to the 4. So fourth root of 16 equals fourth root of 2 to the 4. And therefore, if we have that, so 16 equals b to the 4 for some number b, but we know 16 is equal to the 4, this means that that b is equal to 2. Okay? That b is equal to 2. Okay? So that's the reason why we have 2 in here. Now, let me put this remark in this part. You may argue that 16 can also be written as negative 2 times negative 2 times negative 2 times negative 2. Correct? Because you will have an even power in here. Okay? So negative 2, negative 2, negative 2, negative 2, all those negatives will just cancel each other. And we will have a positive number. Which means that this guy here can be written as negative 2 to the 4. Okay? But why are we not using negative 2? But we used positive 2 instead. Look at the definition. Let us look at the definition again. Okay? So, in here, nth root of a equals b means a equals b to the n, where a is greater than or equal to 0 and b is greater than or equal to 0 if n is even. Okay? If n is even. So both a and b are greater than or equal to 0 when n is even. And we see here, n equals 4. 4 is an even number. So the a, the one inside here, and the b here must be both greater than or equal to 0. So that's the reason why we don't use negative 2. Okay? We don't use negative 2. That's the reason why we only have this guy here, 2 to the power 4. Okay? So question for this particular example. This is just the first example. So this one should be easier. Okay? Next example here. We have the cube root. Okay? Cube root of 1 over 27. So again, if we have, say, cube root of 1 over 27, this is equal to b, and this means that 1 over 27 must be equal to b to the power 3. Okay? B to the power 3. But we know 27, it's equal to what? 3 times 3 times 3. So 3 times 3, it's 9. 9 times 3, that's 27. Okay? So we know that 27, this is equal to 3 times 3 times 3. Or this is equal to 1 over 3 to the power 3. But the numerator here, it's 1. And any power of 1 will still give you 1. So we can just put 1 raised to power 3. And therefore, this is equal to 1 over 3 to the power 3. Okay? And that's what you see in here. Cube root of 1 over 3 cube. Okay? And now, from this definition, it means that. So it means that our b is equal to 1/3. This b here must be equal to 1/3. Because 1/3 to the power 3, that's equal to 1 over 27. Okay? Question. Okay. Next example in here. Now we have fifth root of negative 243. Okay? Fifth root of negative 243. So using the definition again, we have the fifth root of negative 243. This is equal to b. And this means that we have negative 243 must be equal to b to the power 5. Okay? So if it is b to the power 5, this means, or this negative 243, that can be written as, so judging from this equality here, that negative 243 is equal to negative 3 times negative 3 times negative 3 times negative 3 times negative 3. So we are multiplying negative 3 by itself or with itself 5 times. 1, 2, 3, 4, 5. Or simply, we have negative 3 to the fifth power. Okay? So from this equality here, it means that our b must be equal to negative 3. And if we write it this way, we have fifth root of negative 243. This is equal to the fifth root of negative 3 to the power 5. And this is now equal to negative 3. Okay? So from these three examples, it looks like the index here, if it is the same with the power inside the radical sign, okay, if they are the same, it looks like they just cancel each other. So we have index here equals 4, and then the power of 2 here equals 4. Then they just cancel each other, and therefore we get 2. Similarly for this, we have the cube root, okay, cube root here. And then we have 1/3, and then there's a power 3. They just cancel each other, and we have power, we have 1/3. And same with this guy here. Okay? Now, for the fourth example here, this is what we have. Fourth root. And look at this. Negative 6 to the power 4. Okay? Negative 6 to the power 4. So what does this mean? We have fourth root of negative 6 to the power 4. This is equal to sum b. And this means that negative 6 to the power 4 equals b to the 4. Now, I want to remind you that some students will have some errors in here. And this is a common mistake. Some students will do this. Therefore, some students will do this. Therefore, b must be equal to negative 6. Okay? Now, I want to tell you that this is not correct. Okay? Why? Remember our remark? If the index is even, okay? If the index is even, the radicand, okay, or the one inside the radical symbol must be positive or must be greater than or equal to 0. And also the b must be greater than or equal to 0. Okay? Now, look at this. Sir, I see negative 6 there. But take note, you have negative 6 indeed, but you are raising it to power 4. Okay? And remember, if you have a power that is an even number, the negative doesn't matter. It just disappears. Okay? Okay? So what does this mean? This negative 6 to the power 4, this guy here, let me go to this direction. This guy here, it's what? 36 times 36. Okay? Or simply, this is 1296. 1296. If you multiply negative 6 with itself 4 times, okay, you will get 1296. And it's a positive number. Okay? So this is what we actually want. Fourth root. Fourth root of 1296 must be equal to b. And this means, that 1296 equals b to the 4. Okay? And 1296 is a positive number. Okay? And as I have mentioned, if your power is an even number, then the negative doesn't matter. It just disappears. And this 1296 here is actually equal to 6 to the 4. Okay? So in here, what you actually see here, fourth root of negative 6 to the 4, that is equal to positive 6. Okay? So this b here, it's, or this 6 here, it's the b in here. Okay? That's why we have equals 6 in here. Okay? Now, what is this symbol? This symbol here is read as, so let me just write it here. So this guy here, it's read as, so read as absolute value, absolute value, okay, absolute value of negative 6. Okay, absolute value of negative 6. And what is this absolute value? So let us recall, absolute value of a number, it just brings everything to positive. Okay? So if your number is positive already, the absolute value of that number is the number. Okay? Is that number. But if your number is negative, okay, then the absolute value of that negative number becomes the positive counterpart. Like this guy, negative 6, you get the absolute value. The positive counterpart of negative 6 is positive 6. Okay? So, look at this. 4 here, index, power 4 here, it looks like they just canceled each other. That's why we just get that this guy here. Similarly for this, cube root, and then 1/3 to the power 3, it looks like 3 and 3 just canceled each other to get this 1/3. In here, you have fifth root, okay, 5 and 5. Fifth root here, and then negative 3 to the power 5. It looks like they just canceled each other to get negative 3. But be reminded when similar to this case, you have even root, okay, even index, and then the power, of course, if the same as that, we actually get the positive counterpart if we have a negative inside here. Okay? Okay? So, in general, we have the following. If n is greater than or equal to 2 and is an integer and a is a real number, we have the following. The nth root of a to the n. So n index, power of a is n. The nth root of a to the n, this is equal to a. So it looks like this n here and this n here canceled. Okay? If n is an odd number greater than or equal to 3. Take note of that condition. On the other hand, nth root of a to the n. Nth root of a to the n, this is equal to the absolute value of a. Okay? Absolute value of a if n is even. So again, nth root of a to the n, this is equal to a if n is odd. And nth root of a to the n equals absolute value of a if n is even. Okay? So this is one of the examples for this. N is even. That's equal to 4. So roughly, if we follow that definition, this guy here must be equal to absolute value of positive 2. But this is already positive, so we just have that positive 2 in here. Here, 3 is odd, so they just canceled. We just copy 1/3. Here, 5 is odd. Okay? So fifth root of negative 3 to the 5, they just canceled. We just copied negative 3. Here, 4 again, 4 is even. But notice, instead, we have here negative number raised to power 4. So we use the absolute value of negative 6, and that's equal to 6. Okay? So before I proceed, let me just write here let me just recall the definition of absolute value of the number a. So I already mentioned earlier, it's just the positive counterpart of a. If a is already positive, then we just copy a. If a is negative, we remove the negative sign. So roughly, this is the definition. That's equal to a if a is greater than or equal to 0. And we have negative a if a is less than 0. Okay? So what's happening in here? Why we put this negative? So if a is negative, a will have its own negative sign. So if I put the negative here, this negative sign here will remove the negative sign of a. To understand this better, okay? To understand this better, the example here, you have negative 6. This is equal to negative of negative 6. So absolute value of negative 6, this is equal to negative of negative 6. So a, it's equal to negative 6. It has its own negative sign. So I put that negative outside a. So that's your negative outside a, and a is negative 6. So negative times negative, this gives you positive 6. Okay? Another example, say you have negative 11, and we want the absolute value of that. So this is equal to negative of negative 11. So again, negative and negative here just cancel each other. You have positive 11. If you have absolute value of 21, 21 is already a positive number. So this is just 21. Okay? Question so far. Okay, so this is a good question. What happens if the power is odd and the index is even? We'll see later. Okay, we'll see these cases later. Okay? And it doesn't need to have the same index and power inside. Okay? It just so happened that if they have the same, so this guy here uh, tells us that if the index is the same as the power inside, they just cancel each other. They just uh, reverse each other's work. Okay? So 2 to the 4, 2 to the 4, it means you multiply your 2 with itself 4 times. Okay? And then fourth root, it reverses the process of that exponentiation. Okay? It reverses the process of that exponentiation. Other question? Now, let us look at some properties here. So the properties that you will see here are very much similar to the properties of exponents. Okay? Properties of exponents. So first, the nth root of a, b, okay? The nth root of a, b. So you have a product inside the radical symbol. You can separate them. So nth root of a, b, this is equal to nth root of a times nth root of b. Okay? So we can distribute. We can distribute the radical symbol over a product Take note of that, over a product. So we have the multiplication, we have the division. Nth root of A over B, okay? Nth root of A over B, this is equal to nth root of A divided by nth root of B. So we can distribute this index or this radical symbol or radical signs. Okay? Now look at this. You have nth root of A to the M. Nth root of A to the M. So this partially answers the question earlier. So nth root of A to the M, this is equal to nth root of A raised to power M. Okay? So nth root of A to the M, this is equal to nth root of A to the power M. Okay? So let us apply these properties. First example here, we have square root of 18. So take note, there is no index here. It is assumed to be 2. That's why we have square root of 18. Now, 18 can be written as 9 times 2. Okay? It can also be written as 3 times 6. 18 can also be written as 3 times 6. Okay? But we are going to use this 9 times 2. Okay? We are going to use this 9 times 2. Now, we have a product, 9 times 2. We want to get the square root of 9 times 2. It's the same as this. Which means that this square root of 9 times 2 can now be written as square root of 9 square root of 2. Okay? Square root of 9 square root of 2. Now, take note, 9, that's equal to 3 squared, or 3 times 3. This 9 here, it's equal to 3 squared. So I can now rewrite square root of 9 as square root of 3 squared. And notice, there is an invisible 2 in here. There is an invisible 2 in here. Okay? So index is equal to 2, power is equal to 2. They just cancel each other's work. Which means what? This guy here can simply be written as 3, while square root of 2 remains as is. Okay? So you have 3 square root of 2. Okay? So let's go back to the question. Why did we not use 3 times 6? So you can write this as 3 times 6. Okay? You can go from this direction following this property here, square root of 3 times square root of 6. Okay? And at this point, there's nothing to do. But remember this, 6 here is 3 times 2. So you will have what? Square root of 3. That's your square root of 3 from here. And then your 6, it's 3 times 2. Okay? And then you use this again. You will obtain square root of 3 from the first square root of 3. And then you have the square root of 3 times square root of 2 again. Okay? And now you will see this guy. You will see this guy. You will get square root of 3 quantity squared square root of 2. And this guy here, we can use this. Okay? We can use this. Or simply, if we know the power is equal to 2, the index is also equal to 2, they cancel each other's work, which means that you will still get 3 in here, and then square root of 2 remains as is. Okay? But notice the added step. Unlike in this, you factored 18 as 3 times 6. You use your property here, but eventually you realize 6 is 3 times 2. So you have written it this way, and then you now have square root of 3 times the square root of 3, or we have this. So there is an additional step. Okay? Of course, I am not saying that this step here is easier to use than this step here, or this line here is easier to follow than this line here. It's not like that. Okay? You will arrive at the same answer whatever path you're going to use. It just so happened that I know 9 is a square of something, and I am taking the square root. So I can immediately use the previous slide, the remark in the previous slide. Okay? Question. And take note, in here we have square root of 2, it remains as is. Okay? So, this is one of the examples why calculators are not actually being used in this course. Because you will not use calculator in order to solve square root of 18. The final answer must be written this way, and this will not be converted to decimal. I think I have remarked that before. But if numbers are written as is, and you know you can convert it to decimal, you don't convert them to decimal. Rational expressions or rational numbers, you can convert it to its lowest term, but not in decimal form. You can just reduce it to lowest term, but not convert it to decimal form. Same is true with these numbers, square root of 2, other square roots without perfect square inside the radical symbol, etc. Okay? Question. Next, we have square root of 18, cube root of 5 over 24. Okay, cube root of 5 over 24. And 24. In here we use this. So cube root of 5 over cube root of 24. Now, 24 can be written as 8 times 3. Now, I am using 8 times 3. We could have used 6 times 4, etc. We can also use 12 times 2. But I am using 8 times 3. Okay? And the reason is, we are taking the cube root, and I know 8 is a perfect cube, meaning it is a cube of something. Okay? So for this denominator here, we follow first this property here to write it as cube root of 8 times cube root of 3. Okay? Cube root of 8 times cube root of 3. Now, cube root of 8, as I have said, 8 is a perfect cube. It can be written as, so your 8, oops, what happened there? Let me just go back to that slide. Here. So 8 can be written as 2 to the power 3. Which means cube root of 8, this is equal to cube root of 2 to the power 3. And therefore, 3 here cancels with the 3 here. We'll just get 2. Okay? So what does this mean? Cube root of 8 can now be written as 2. And therefore, look at what happened in the denominator. Okay? Okay? So the reduced form or the simplified form, a simplified form for this, it's equal to cube root of 5 all over 2 cube root of 3. Okay?
Sir, could you go back to what you were
Okay.
writing?
This guy.
Yeah, that's it.
Okay.
Okay, sounds good. Thank you.
You're welcome. So look at this. I said cube root of 5 over 24 can be simplified into cube root of 5 over 2 cube root of 3. This guy here, I must tell you that this guy here is not the simplified version we want. Later, what we're going to do is when we see radicals on the denominator, we want to rationalize it. Okay? So I will discuss that later in the lecture. For now, let us leave the thing in this guy here in this form. Okay? Next example. We have cube root of negative 81 x to the 5. Okay? Now, cube root here, this is an odd number. Okay? Negative, it's just fine because this is an odd number. X can be any number. Okay? If x is a positive number, the whole guys here or the whole expression here, the radicand, it's a negative number. It's defined in cube root. Or when we cube root that negative number, we'll still get some number. If x is a negative number, we will get something positive in here. Okay? And it's just fine to get the cube root of that positive number. So in here, x can be anything. Okay? X can be anything. Now, what we're going to do with this is the following. Negative 81, it can be written as 9 times 9. Okay? So, sorry, negative 81, this can be written as negative 9 times 9. Okay? And this guy here, 9 can be written as 3 times 3, 3 times 3. And therefore, the other 9 here, we can still write it as 3 times 3. And there's a negative in here. Okay? And this is cube root. So what we're going to do is to get the 3 3's in here. Okay? The 3 3's in here. Which means that we can write this negative 81 as 3 or negative 3 to the power 3 times 3. That's what we can do. But we have negative here and the power is odd. Okay? The power is odd. We can put this negative inside, which means that this guy here is the same as negative 3 to the power 3 times 3. Okay? Is everyone good? Now, this is what we are targeting. This is what we are targeting. To write that negative 81 as negative 3 to the power 3 times 3. Okay? But this negative 3 to the power 3, you can write it as, so negative 3 to the power 3, this is equal to negative 27. Negative 3 times negative 3, that's positive 9, times negative 3, that's negative 27. Which means that negative 81, we can separate it into negative 27 times 3. Or we can decompose negative 81 as negative 27 times 3. Now look at this. X to the fifth power, our index here is 3. So what we're going to do is to write x to the fifth power as x to the 3 times x squared. Because this is just one of those ways to get the same index. We have x to the power 3. Okay? So you will see next that x to the 5 is decomposed into x cubed x squared. So here, we have cube root of negative 27 x cubed times 3x squared. So remember, we have written negative 81 as negative 27 times 3. And negative 27, it's negative 3 cubed. So that's why we wrote negative 27 beside x cubed, and 3 is beside that x squared. Because now, this expression here, negative 27x cubed, can be written as negative 3x to the power 3. Correct? So negative 27x cubed, this is equal to negative 3 cubed x cubed, and therefore, laws of exponents tell us we will have negative 3x quantity cubed. That's why we have this guy. And at the same time, this is this guy times this guy. We use this property here. So we can separate them. Okay? And now, index equals 3, power equals 3. So they just cancel each other. We will get negative 3x because this and this just cancel each other. We have negative 3x. And then this guy, we still have cube root of 3x squared. Okay? So meaning we cannot work on this anymore. Okay? And later I will remark when do we know if we can still reduce these radical expressions. Okay? Questions so far? Okay. Let's have this guy. You have fourth root of 16x to the 6. 16x to the 6. Now, this is even index, okay? And we have a variable x, but that variable is being raised to power 6. So any number raised to power 6 or any number raised to an even power will give us positive number. So whatever x is, we'll still get positive inside here. Meaning your x can take any number. Okay? Your x can take any number. Okay? Now, what do we have? We have 16 here, but 16. 16. This is equal to 2 to the power 4. You can write 2 times 8. You can write 4 times 4. But let us write it as 2 times 2 times 2 times 2, or 2 to the power 4. We use power 4 already because the index here is also 4. So later, they will just cancel each other. Furthermore, your x to the 6, we decompose this into the following. X to the 4 times x squared. And we are using this decomposition because, again, we have fourth power, and this guy here gives us fourth power. Okay? Meaning, we have the following. So 16, we attach it to the x to the 4, and then leave x squared somewhere there. And then 16, we separate using this guy here. Okay, we separate using this property here. And then 16x to the 4 can be written as 2x to the 4. As I have said, 16, it's 2 to the 4. So 16x to the 4. So this guy here, it's just 2 to the 4 x to the 4. And this guy here is now this guy. Okay? So these 4 and 4 that just cancels each other. Okay? And therefore, we have the following. Absolute value of 2x, fourth root of x squared. Okay? Absolute value of 2x, fourth root of x squared. Now, you might ask, why did this absolute value symbol appear? It's because, again, since in the original question or in the original problem, this x here is raised to power 6, and any number raised to an even power will give you positive number. So x to the 6 will always be positive, and we will not have any problem with that. But therefore, in here, x can take negative numbers also. Okay, x can take negative numbers also, which means we have to make this positive because we are following the remark. If the guy inside the radical symbol is positive, the b, the b must also be positive. So again, here you have a. So we have here, let me write even. So a equals b. Okay. In this, we have the condition a greater than or equal to 0 and B greater than or equal to 0. We are sure that this guy here is positive, so the fourth root exists. We have to make sure that this guy here is positive. So we have to do the absolute value thing. Okay? Because if we don't put that absolute value thing, this absolute value symbol, your x here can take negative number. So if x is negative number, then 2x will also be a negative number. And therefore, this will not be satisfied. Okay? Question? Question? So in here, in the last item, the radical can still be simplified. So in here, this can still be simplified. And later we'll talk about that. So there is a question here. How will they take negative number if both are even? What do you mean even? The 4 is even, the 6 is even. Okay? 6 is even. Therefore, look at this. Just for an example, negative 1 to the 6, this is positive 1. Negative 2 to the 6, this is what? 32? 64? Negative 2 times negative 2. So that's 4. 4 times 4, 16 times 4, 64. It's a positive number, correct? So your x can have positive, can take negative number. We are sure 16x to the 6, it's always positive. Whatever your x is. But in this guy, if you removed that negative or that absolute value symbol and you put x equals negative 1, then you will get negative number in here. So that's how they will take the negative. That's how this number here can take negative. Okay? Other question? Now, similar to exponents, we have this. We have this inequality. Nth root of a plus b. This is not always equal to nth root of a plus nth root of b. So remember, you have your a plus b to the n. This is not the same as a to the n plus b to the n in general. There are only special cases where equality holds. But in general, the equality does not hold. Okay? For an example here, we have square root of 2 plus 2. 2 plus 2, that's equal to 4. And square root of 4, that's equal to 2. Because 4 is just 2 squared. Okay? So what if we do this right-hand side here? We have square root of 2 plus square root of 2. If you use your calculator, this is approximately equal to 2.828. So these guys here, they are not equal. So equality does not hold in general. Okay? Next, however, radicals can be combined if they have the same index and same radicand. We call them like radicals. So remember when we discussed monomials, we can combine monomials if they have the same variable and same exponent. So analogously, like radicals is when the radicals have the same index and the same radicand. So this is one way to simplify radical expressions, combining like radicals. So for example, in here, we have square root of 8 minus 3 square root of 32. So we have fourth root of 32x minus fourth root of 2x to the 5. Okay? So look at this. In the last example, observe that x cannot take negative numbers. Just like what I have explained off the record. Now, when we have radical expressions, we want we want to do simplification of our rational radical expressions, or if when we see radicals in the denominator, okay, we want to remove the radical in the denominator. Okay? So when radicals occur in quotients, it is customary to rewrite the quotient so that the new denominator contains no radicals. Okay? The process is called rationalizing the denominator. So meaning if we have radical expressions in the denominator, we want to remove the radical signs. And the process we are doing is called rationalizing the denominator. When rationalizing a denominator, the following identities may be helpful. First, we have this. A minus b, this is equal to a, the square root of a plus the square root of b times square root of a minus square root of b. It's like difference of two squares. Let us look at this side here. Okay, so difference of two squares formula tells us that this guy here, it's equal to square root of a squared minus square root of b squared. And we've been doing this, square root of a squared. The square root just cancels the square here. Similarly for this, square root cancels the square there. So you will get your a minus b. So you have it here. Okay. Of course, we are assuming that your a is some positive number. So that square root of a exists. And b is some positive number. So the square root of b exists. So this is the counterpart for difference of two squares. We also have some counterpart for sum of two cubes and difference of two cubes. Okay? So a plus b can also be written as square root of a plus square root of b times, sorry, cube root of a plus cube root of b times cube root of a squared minus cube root of a cube root of b plus cube root of b squared. And a minus b can also be written as cube root of a minus cube root of b times cube root of a squared plus cube root of a cube root of b plus cube root of b squared. Of course, these two guys here possibly is difficult to or are difficult to memorize. So if they will be needed during your exam or quiz, I will write them. But for these guys here, I can leave it, okay? Because again, this just came from difference of two squares, and these two guys here came from difference or sum of two cubes, okay? So these two guys here are more difficult to memorize compared to this guy here, okay? Let us now consider several examples here. So rationalize the denominators of each expressions. So for this, 2 over 5. 2 over 5. So for some grammar Nazis, let me just remove this. So anyway, 2 over square root of 5. So there is a rational or radical expression in the denominator. Okay, we have square root of 5. So to remove this radical here, we can multiply and divide square root of 5 to this expression here, so that we will have the following. So 2 over square root of 5 times square root of 5 over square root of 5. Because again, if we multiply square root of 5 with itself, you will have square root of 5 quantity squared, and then the square root and the square will cancel each other. So if we do this, we will have the following. So 2 square root of 5 over square root of 5 squared, and therefore we have 2 square root of 5 over 5. So we have removed that radical sign in the denominator. Okay? Next example here, 6 over 5 cube root of 3. So look at this. You have cube root of 3 in the denominator. We can multiply cube root of 3, but what will happen to that? Cube root of 3 times cube root of 3 will only give you cube root of 3 squared. Index is 3, but the power inside, it's just 2. So instead of multiplying cube root of 3 only, we multiply cube root of 3 squared. Okay? So we multiply the denominator by cube root of 3 squared. We also multiply the numerator by cube root of 3 squared. And therefore, if we multiply cube root of 3 times cube root of 3 squared, we will get cube root of 3 cubed in the denominator. Okay? And therefore, the 3 here and the 3 here will cancel each other. And of course, in the numerator, you just multiply your 6 with cube root of 3 squared. And in here, there's nothing to do because the index is 3. Okay? The power inside here, it's just 2. We can simplify radicals. Okay? For example, in this guy here, if your index is greater than the power in the radicand. So index is greater than the power in the radicand. We cannot simplify that possibly. Okay? And another possibility that we can simplify is when the index and the power inside have common factors. Okay? Have common factors. So later we will see that. So in here you have index 3, power 3, they will just cancel each other. So you will have 3 here, and then 5 times 3 will give you 15. Correct? Because the 3 here and the 3 here cancels. The index 3 and the power 3 cancels. So you will have 5 times 3, and 5 times 3 is 15. And then 6 over 15 can be simplified further into 2 over 5. So that this guy here is 2 cube root of 9 over 5. Okay? Yes, question?
Yeah, I'm kind of confused how in the middle you have 3 cubed with the cube root 3. I really don't understand how that happened. No, in the middle part, yeah. On the
Yeah,
right side, how? No.
because you have here cube root of 3, and then you have here cube root of 3 squared. Okay?
But where do you get the 3 squared from?
It's the number that we want, that we will use in order to remove this radical sign. Okay? So, say you have something like this. Let's pick specific number. Say you have, for example, in this case, square root of a. So roughly there is an invisible 2 in here, correct?
Mm-hmm.
There's an invisible 2 in here. So to remove that, we need a to have power 2. So
Mm-hmm.
I'll multiply this with square root of a, which will give me square root of a quantity squared, or you have square root of a squared. And therefore, you can now cancel the effect of square root and the effect of uh, the square here. So you will get your a.
Oh, okay.
So
All right.
same thing for the cube root. You have cube root of a. In order to cancel this 3 here, your a must have power 3. Must have power 3. But a only has power 1. So we need power 2. We need power 2 more. So that's why we will multiply. We will multiply cube root of a squared. So the power here, okay, the power here will be added to the power here. So you will get your cube root of a to the power 3. And now you can do the cancellation of fx. Cube root and then power 3, you'll just get a. So that's what we do in here. So you
Oh,
have 3 power 1 missing power 2. We are missing 2 powers of 3. I mean, to get
okay.
that cube root of 3 cube. Yeah, so we chose that specifically.
Okay. Thank you so much.
You're welcome.
Sir, I got another question.
Yeah.
So at the last part, there's where? How did you simplify 15 to 5?
Because you have 6 here. Your 6 is actually 2 times 3. Your 15 is 5 times 3. So 3 can cancel each other.
Oh, okay.
Okay? That's why we get 2 in the numerator and 5 in the denominator.
Okay, thank you.
Questions? Yeah, you're welcome. So in this case, we just multiplied some radicals. Okay? Some radical, multiply and divide some radical, or multiply both the numerator and denominator by some radical without other numbers or other part. Let us look at the following example here. So 2 minus square root of 5 all over 2 plus 3 square root of 5. So we want to rationalize the denominator. Next problem, rationalize the denominator. So we have here square root of x plus h minus the square root of x over square root of x plus h plus square root of x. So let me just give a remark in this. The reason why I want this example is when you go to your Calculus 1 class. So when you proceed with your Calculus 1 class, you will see a lot of expressions in this form. You have something x plus h, okay? Or in other classes, you will see x plus delta x, okay? So that's the reason why I want to put this example in here, okay? So let us work on this example. Now, here are some more properties. It is easy to view radicals using the following definitions. If A is a real number and n is an integer greater than or equal to 2, then the nth root of A is actually A raised to the power 1 over n. Okay, so let me rewrite that for emphasis. Nth root of A, this is simply A raised to power 1 over n, provided nth root of A exists. So meaning, radicals are simply exponential expressions. And we have properties of exponential expressions with integer exponents. Same properties hold. So before we discuss integer exponents, now we can discuss fractional exponents. Okay? And we also have the following remark. If A is a real number and m and n are integers containing no common factors, take note of that, no common factors with n greater than or equal to 2, then A raised to m over n equals nth root of A to the m, and then from the previous remark, this guy here is the same as nth root of A to the power m. Okay? So again, for emphasis, let us rewrite that. So A raised to m over n. So that's the exponent of A. It can be turned into radical symbols. So that's the same as nth root of A to the m. So A to the m is inside nth root, or your nth root of A, the nth root of A is raised to the power m. Okay? So again, provided that nth root of A exists. Okay? And this property here, a to the r, a to the s, that's equal to a to the r plus s. And a raised to negative r, that's equal to 1 over a to the r. So we just recall the property of exponents, properties of exponents that we discussed in the beginning of our course. So now we can convert radical expressions into exponentials, or we can have exponentials with fractional exponents to radicals. Okay? So now let us work on simplifying expressions, okay, with the use of these radicals, or with the use of exponents with fractional, or exponentials with fractional exponents. So first example, so we want to simplify the expression, express your
Sir,
answer
could you
so
go back
that,
a slide, please?
yes, question?
Yeah, could you go back a slide, please, for one
Sorry,
second?
so you have this.
Yeah. All right, thank you very much.
Okay. So we want to simplify the expression, express your answer so that only positive exponents occur. So we have these rational expressions combined with exponents with fractional exponents, or exponentials with fractional exponents. Next example, we have x plus 4 raised to 1 half minus 2x times x plus 4 raised to negative 1 half all over x plus 4. This will be the last example for this lecture. So we have this 1 plus x squared over 2 square root of x minus 2x square root of x all over 1 plus x squared squared. Just work on as many problems as you can on pages 34 to 36 of the 016 module. Okay?